that's it. Tuesday. We stay with this kind of a change of variables problems for the last part of this chapter. And then we quickly go to the chapter 15. Okay, I don't give you any question from chapter 15 on the coming test, but we probably get time to start that chapter tomorrow. But no question from that one. I review on Thursday, but no question from chapter 15 on test 3. Okay, because chapter 15 is quite different, and it's not difficult, much easier than the other one. Okay, so I want to make sure I give you a hint for that last example that we did. See this one? We did it with the spherical coordinate, but if you're given the choice, you can do it using the cylindrical coordinate. I'll show you the cylindrical one as well, so that in case you see it, then you can pick a good choice. Yes, I didn't talk about that. Wanted to see it. Okay, so I'm going to continue with this example again, but this time, if you are going to be decide, so sometimes you have to decide which method are going to be the one. So you can use the cylindrical one. So if they just say evaluate this integral, okay, this is it. If you want to just evaluate the integral, and the same thing that we did have, it's going to be -1 to 1. Okay, and you get a -1 minus x squared, just the circle part. And the last part was radical x squared plus y squared to 1, and that's your dz, okay, dy dx. You see, if you want to pick a choice, if you are going to be two-dimensional, you see, in two-dimensional, that's a polar form, because that's a semicircle. Okay, this is circle, full circle. Then, and this expression in the polar form, x squared plus y squared is simply r squared. So the best method to do this one in the triple one is cylindrical coordinates. Okay, I did it a spherical one because I wanted to show those techniques. But if you want to do it, this is going to be okay. So what we're going to do is we are going to use the cylindrical method. Okay, cylindrical method. So for the cylindrical method, this is it. We have the x between -1 and 1, and we have the y, which is nicely seated between this semicircle. Okay, that's it. And the other part, of course, going to be your z. Your z is between x squared plus y squared, and this is z. Okay, so we focus on this part. Y is equal to the positive negative to get the cross section. Okay, and you know that this would give you x squared plus y squared equal to 1. Okay, which is going to be a unit circle. So we have the unit circle over here, and you know it right away. This is going to be the unit circle. And since x goes from -1 to 1, this is -1 to 1. Okay, and this is a positive negative, so the full circle is going to be the region. So we have a full circle in polar coordinates. Your r is between 0 and 1 because of the radius, and your data is going to be between 0 and 2 pi. So easily that can be done. Okay, and in the case of the z, that would be again easy to operate. So the z is radical x squared plus y squared less than z less than equal to 1, and this would change into, you know that this would change into the r squared. And so your z is simply between r and 1. You see, so that's a best choice for this integral. So we go back and we change it, and it can be done easily. So this is it. So the integral now would be changed into, we change it to the polar. This is going to be the polar. Okay, and this is your data, 0 to 2 pi. This is your r, which is 0 to 1. And this is going to be your z, which is going to be from r to 1. Okay, there is an extra r, and the rest is going to be dz, dr, d data. Okay, any question? So as you can see, this integral is much easier to handle rather than the one that we did the other day. And so we go with the z first. So it's going to be 0 to 2 pi, and you have the 0 to 1 simply rz, and the z between r and 1, then the dr, d data. Okay, so substitute. So that give you 0 to 2 pi, 0 to 1. If you put the z equal to 1, that give you r minus. If you put z equal to the r, so that give you r. Okay, that's it. And then you get the dr and the d data. Okay, so this is going to be a situation we're going to have. So simply, this would simply r minus r squared. So it's going to be 0 to 2 pi, okay, 0 to 1, r minus r squared, and dr, d data, and easily integrated. So you have r squared over 2. Okay, then you get r cubed over 3, and to be evaluated from 0 to 1, and when you're done, d data. So it's going to be 0 to 2 pi. If you put the 1, that gives 1/2 minus 1/3. Okay, 1/2 minus 1/3, d data. That would be 1/6. Okay, it would be 1/6. So 0 to 2 pi, 1/6 of the data. So it's going to be 1/6 of the data. Okay, and this is between 0 and 2 pi. So we get the 2 pi 6, which is pi third. Okay, and you saw the other day, we have such a long procedure to get this one, the same one. So that would be much easier to prove this. But the other method was interesting. It was interesting to learn something. But if you see it, cylindrical method, this is the best. Okay, any questions? So that special example, this is kind of a problem in your book. I've given this one several times on the test. Okay, the people, they miss it. So I want to explain where are you going to miss this one. Is it like the surface area that you did on the quiz that I have to check it to see if you missed that one too? Because this is the cross section when you drop it down in 2-dimensional for these integrations. Sometimes if you have two solids, if you like, and the area in between, you got to be careful when you check the z. Okay, are you done? No, this is the one. None of the problem in your book, in your assignment, and it's it's all over the places in any calculus book. You must have this one. So what is this? It's a volume problem, but the 3-dimensional solid that you have is going to be bonded by 2 other solids. Okay, so one of them in this case is a sphere, the other one is a coin. Okay, so they just change it, but the foundation of the problem is going to be the same. So find the volume. Okay, find the volume of the solid G, call it solid G, bonded above. Okay, it's going to be bonded above. It's going to be bonded above by a sphere, by the sphere with this information. Equation of your sphere is x squared plus y squared plus z squared equal to 60. It's going to be a square. centered at 0 radius of 4, and you see bounded below, and bounded below by the coin. It's going to be the ice cream coin. The coin is going to be z equal to the, okay, that's it, x squared plus y squared. Okay, so this is a situation that you are going to have. Okay, it's going to be like, like the kind of the it's going to be the ice cream, and you may think about the top is going to be just a sphere somewhere over there. Okay, so if you take it into the situation we're going to have, so to get the volume, of course, we use the triple integral to get that volume. So what's going to be the formula for the volume? So we start with the volume formula. You see again this one, solution. So the volume is V equal to, if you do it with the triple, so the dV would represent the volume. So you cannot carry any other function, or don't need it. You see 1, 2, 3 on the W, the region that we're going to get, and then you put the 1 here and the dV. You see that's going to be the formula for the volume for the triple integral. The volume can be also done with a cylindrical one. If you go with the cylindrical one, you need a function here. Sorry, you can do it with the double integral. If you go with the double integral, this is going to be dA, which is going to be the differential of the area, and you need the height, which is going to be your function. You multiply them together, and then that gives you. So in this case, you better do the triple. Okay, the triple integral is the appropriate one for this one. Now, what is the catch? The catch is going to be, you have to identify the limit of the integrations. So you have the x, y, z. So the first thing to do, you see the z's, that's z given, the surfaces. So in this case, it's going to be the region between these two, if you like, or the one that you're going to have. Okay, it's going to be bounded above by these two. So if you want to find the restriction of the z, the top z is going to be like the sphere, the bottom z is going to be the coin. So in this case, so your z basically, and when you write the z, okay, your z must be a function of x and y. You solve for z basically. This is z, so you have to solve for that one for z2. You see, this is going to be a situation you're going to have. You already got the z on the top, on the bottom. So that's one of the value of the z that you are going to use. So you have to take care of the z of the sphere. The z of the sphere is going to be x squared plus y squared plus z squared equal to the 16. You can solve for z and get the positive part. So this would be z squared equal to the 16 minus x squared minus y squared, and take the positive square root. So that z would be 16 minus x squared minus y squared. Then you can say that your z now is going to be between these two. Okay, and so from the bottom, below is the coin. Okay, below is the coin, and above is just the hemisphere, if you like. It's going to be 16 minus x squared minus y squared. So this is how you arrange it. Okay, you arrange the z numbers. Any question? That's a z. Now, the difficulty for this one is when you drop it down. So in order to get in order to get the other part, you have to project this region into the two-dimensional. The projection that we usually do is we replace the z by 0, and that's where the people make a mistake on the test. So what they do is they replace this z by 0, and they focus on the x squared plus y squared to the 16, which is not correct, because you have two two solids. Your region, okay, also going to be bounded by these two, the top and the bottom. So what you have to do is, instead of putting z equal to the 0, you have to eliminate the z between these two. That would result in an equation in x and y, and that equation is the one they're going to take as your cross section. Okay, so make sure you are not going to make a mistake on this one. So if you like, this is going to be a kind of projection. Okay, projection on XY plane, if you like, that you want to take for your two-dimensional. So you have to eliminate this z rather than putting z equal to the 0. So this is going to be the case. So we have the z equal to the, again, radical x squared plus y squared on the top. Then you have a z equal to the radical 16 minus x squared minus y squared. Now eliminate the z, just like a substitution method type. So you let them equal to each other. Okay, and this is going to be 16 minus x squared minus y squared. And if you square it, that gives an equation in x and the y. You know that the projection is going to be a circle when you think about it as a two-dimensional one. Like a shadow of this down here. So it's going to be x squared plus y squared. And this is going to be 16 minus x squared minus y squared. Okay, you can see the difference. Now, if you move these x squares to the other side, okay, so it's going to be x squared plus, I write it so you know what I'm talking about. You see, this is going to be the case. So you are going to end up with the 2x squared plus 2y squared equal to the 16, and you get x squared plus y squared equal to 8. You see, this circle is going to be the shadow or the projection into the two-dimensional. Any question? So most of the people on the test, they find out that the projection is going to be a circle. So what they do, they replace the z by 0 in the sphere. They got the circle, x squared plus y squared, because they cannot do it with a cone. So they consider x squared plus y squared to the 16, which is not correct. Okay, now that's it. This is going to be the projection. Now we can, different way to do it, we just stay with the rectangular coordinate for the time being, then we decide what we want to do with it. This is going to be the projection into the xy coordinate. And as you can see, this is going to be what? It's going to be a circle, r squared equal to the 8. So r would be 2 radical 2. So your projection in two-dimensional is going to be what? You have a circle. Okay, this is going to be a circle that you have. But your circle is going to be, the radius is going to be negative 2 radical 2. 2 radical 2. So officially, if you like this in rectangular form, I stay with the rectangular. And so if I want to stay with the rectangular coordinate, it's going to be x is negative 2 radical 2, and the 2 radical 2, okay, that is the 1, and the y is, the top and the bottom, those semicircle. So this is going to be 8 minus x squared, okay, and this is going to be 8 minus x squared. So if you want to stay with the rectangular coordinate that you have so far, this is going to be, any question? So we project it in two-dimensional. Now we are ready to set it up in rectangular coordinate, then decide which method are going to use eventually to find it. Okay, but it's important to set it up. So this is going to be now the formula for the volume so far. Okay, so your volume is going to be, this is it, V equal to a triple integral that you have. You go with the X, you go with the Y, and you go with the Z. Okay, and you know that there is a 1 here. So this Z is this, the coin and the hemisphere. Okay, that's it. And this is going to be the dz, the dy, the dx. Okay, your y was that semicircle. So negative square root of 8 minus x squared, the positive 8 minus x squared, and your x, negative 2 radical 2, and the positive 2 radical 2. You see? This is going to be the integral that give you the result. Of course, it can be, it would be it's not wise to, you cannot find it, if you want to use stay with the rectangular coordinate, because it's impossible. So you have to decide what you want to do. You see, you have two choices, of course. You can do it cylindrical or you can do it spherical. Okay. So you see, this is circle. So nothing to worry about. So you have the option of the cylindrical or the spherical. You may try a cylindrical. It's easier if you can handle it, because for the cylindrical, you only have to do is change this one into the R, which can be nicely done. Okay. But I explain how you see for the y is the limit of integration for the y, because I know that the projection into the xy coordinate. So the question is how I did get the limit for the y. You see the projection in two-dimensional is x squared plus y squared to the 8, which is a circle. So this is going to be a circle. So x from negative 2 radical 2 to radical 2, then you have to find y semicircle. So you solve for y squared would be 8 minus x squared. So y would be positive negative, the top bottom. Okay. So semicircle on the top, semicircle on the bottom. So you fix one of them. You fix the x, you have to give us the y in terms of the x. Okay, that give you that semicircle. Okay, so let's going back. So cylindrical is easier, but I do both of them for you. So let's do cylindrical, which is easier. Cylindrical method, because everything is nicely given. So for the cylindrical, quickly, we know what's going on in two-dimensional. We already got all the information, so I make it quick. So in the cylindrical, I have this circle, x squared plus y squared equal to the 8. So that would quickly give us the r, the radius of a circle is 2 radical 2. So that would be the r. And using the full circle, okay, using the full circle, so the data is going to be between 0 and 2 pi. Done. You see. Again, for those people who made a mistake, they go with the 16, which is not correct. Okay, so that's going to be the nature. Now z, this is the z, and we can easily change it to the polar coordinate type. Okay, so it just remind you, just do it right away. You can do it over there. This is your z. You may write this one as negative x squared plus y squared. And if you change it to the polar form, you know that this is going to be radical r squared z, and this is going to be 16 minus r squared. So your z is going to be between r and radical 16 minus r squared. That's it. Any question? So we can set up the formula v equal to polar form or cylindrical form. So the polar, you go with the data 0 to 2 pi. You go with the r 0 to 2 radical 2. You go with the z. Z is r square root of whatever you got over here, 16 minus r squared. Extra r, remember, Jacobian. You will see today, extra r, then the dz, dr, d data, cylindrical form. Okay, we have to take care of this one first. This would be rz. So it's going to be 0 to 2 pi, 0 to 2 radical 2, So your integral would be z from r to radical 16 minus r squared. Of course, when we're done the RD data, if you substitute 0 to 2 pi, 0 to 2 radical 2, when you substitute, it's going to be r square root of 16 minus r squared minus rr. Okay, rr, just remind you. Then the drd data. To take this integral, you know that you have to change that radical, and then we get r squared. So 0 to 2 pi, 0 to 2 radical 2 inside, r 16 minus r squared to the half minus r squared dr d data. Okay, integrate it. The only thing that you need is this must be done by u substitution. Okay, this is my u. So I need the u prime to match with the dr for the du. So the u prime would be negative 2r. So I need a negative 2 here. Okay, so what I do is I divide the outside by 2, or the negative 2. This is the way, you know, I do the substitution method. 0 to 2 pi, 0 to 2 radical 2. So I can change this one into, okay. So I just want to do it right away. Okay, because I have to, okay, I don't want to break. Okay, this is it. I'm sorry. I don't want to break it. So it's going to be, this is going to be negative 1/2. Let me just do it step by step. So this is it. This is going to be, sorry. I just want to do it right away, but I want to explain it at the same time for you. So this is going to be a negative 1/2. So that would be negative 2r times 16 minus r squared to the half. Then minus r squared. Then the dr dt. Okay. So now I'm ready for this part so for this part, I have a u to the 1/2 du, which is going to be u to the 3/2 over the 3/2. Okay, because I take this one to be u, you see I take this one to be u. So this would be my du, if you like. So that simply would be 16 minus r squared to the 3/2. And r squared is easy. Okay, so this is it. We get 0 to 2 pi. So this is going to be negative 1/2 for the first part. That's u to the 3/2 over 3/2, which is going to be 16 minus r squared to the 3/2 over the 3/2. That's first part. And this would be minus r cubed over 3. And when we are done, you have to go from, so r going from 0 to 2 radical 2. Then when you're done, we get d data. Okay, everybody happy about this one? You know, just do this integration right away. So I have to simplify it. I simplify 1/2 and 1/2. So the leftover here is going to be 3. Then I substitute. Okay, already. So this is, so I'm going to simplify 1/2 here and the 1/2 here. So the leftover is going to be 3. So this is going to be negative. Okay, so it's going to be equal to the 0 to 2 pi. 0 to 2 pi. I have a negative, and here I have a 16 minus r squared to the 3/2 over 3, and then the rest are going to be just the same. Okay, now I'm going from r equal to the 0 to 2 radical 2, Then I come back, I get that. Okay, it's messy, but it can be fine. It would be fine. So substitute these numbers. So that gives you 0 to 2 pi. Okay, you put the 2 radical 2 first. So it's going to be minus 16 minus 2 radical 2 squared. And then raise it to the 3/2 over the 3. Minus, same thing here, 2 radical 2 to the 3rd over 3. Then it's going to be minus, when you put r equal to the 0. If you put r equal to the 0, so that gives a negative 16 to the 3/2 over the 3 and minus 0. Okay, then we come back and we say d that. We are just substituting. Carefully simplify. 0 to 2 pi minus, what's the top now? 2 radical 2 square. 2 square would be 4. Radical 2 would be 2. 2 times 4 would be 8. 8, 16 minus 8 would be 8. So you get 8 to the 3/2 over 3. Minus, how about this? 2 radical 2 cubed. Okay, this is it. So 2 cubed would be 8. Okay, that's going to be 8. And radical 2 cubed would be, you get the 8 to 16. It's going to be 16 radical 2 over, okay, over 3. I think that's it. Okay, 2 cubed would be 8. Radical 2 cubed would be 2 radical 2. 2 times 8, 16. 16 radical 2/3. That's going to be 1. Negative would be positive. This would be positive. And then 16 to the 3/2. 16 to the 1/2 is 4. 4 cubed, 64. So that gives us 64 over 3. Okay, and then d data. Simplify that a little bit more, and then you're done. 0 to 2 pi. So 8, this is going to be the case. 8 to the 3/2. Okay, we simplify this one to get this true. This is going to be, we can simplify it because 8 to the 1/2 would be 2 radical 2. Again, this is going to be 2 radical 2 to the 3rd. Okay, which is going to be the same as this one. So it's going to be negative 16 radical 2 over 3. And this is a negative 16 radical 2 over 3 plus the 64 over 3. Okay, that's going to be the one. Or, you can use your calculator, 8 to the 3rd. So we are almost done. So it's going to be 0 to 2 pi. These are like the like fractions. You add them together. So that gives a negative 32 radical 2 over 3 and plus 64 over 3. D data. That's it. And now you integrate it and then you're done. Because integrate is easy. That gives you data. So this is going to be 3 negative 32 radical 2 plus 64. Integral would be data from 0 to 2 pi. Okay, from 0 to 2 pi, if you put the 0, you get nothing. If you put the 2 pi, okay, so that would give you times 2 pi. Negative 32 radical 2 plus 64 over 3 times the 2 pi. Okay, that would be the final answer. Now, if you like, you can pull out the 32. So make it to the 64. You see, this is the way you can do it. You can multiply this one inside. So 64 pi 3rd. 64 pi 3rd, and this is going to be 2 minus radical 2. So this would be the volume. Okay, this is, I just wanted to say it. It's one of the problem in your book. And to be able to handle it. And that part, as I told you, that's something that is going to be in some other places, that cross section that you have. Okay, any question? So that was the best choice. But you may be interested in just doing this volume, that part, using a spherical coordinate. I can show you that one quickly too. So it would be good practice for you to see it. But I go with the cylindrical, which is easier. Always cylindrical is easier, of course, than the spherical one. Any question on this one? So let's go back, and it's a good practice. You have to already set it up. Remember the way we did it, our difficulty was this integral. So we did with the cylindrical one. Somebody may say, oh no, a spherical is easier. So we check to see if you are right. Okay, it's not bad, a spherical one. But the algebra involved always a spherical, because you know that those three formulas that you have to substitute to get it, but it's not bad. Because this part is easy, you see, it's unit circle. So in the case of unit circle, you have your data would be unchanged. It's going to be between 0 and 2 pi. Okay, but your difficulty for it is a good problem to check to see how we are going to find that phi for you. I'm going to do it because I know that there are some things that you learn from this one. The result again, which one do you want? This one. So let's say you learn quite a lot if you do it with the spherical. Let me show you the spherical one. Any question on this one? So that's the best choice, of course. But if you want to be more excited with the method, is a spherical one. So again, you have the option because they didn't say anything. So this would be useful for you because they may give you the integral directly. So method 2, okay, remind you the integral that you have. So you have to find this integral. Remember, negative 2 radical 2, 2 radical 2, and this is a negative 8 minus x squared, 8 minus x squared. I need this one. Okay. So this is the one that we evaluated. And we have the dz, dy, dx. So I'm going to try a spherical one. So, you know, what is going to be a spherical coordinate method? Okay, a spherical form, if you like, or method. So for the spherical form, again, you have to focus on this part. Okay, we already done it. So we know that this part is just x squared plus y squared equal to the 8, the circle. So as soon as we get the circle, then we got the phi. We got the data. So it's a full circle. It's a full circle. So the data is going to be between 0 and 2 pi. So this is the best we can get. Okay, for the rest, of course, you have to focus on your z part and to see what is going to be the range for the row. Remember, for the row, and the range for the phi. That the polar form only give you the data. So we check to see what is the situation that we're going to have. So note that what is your case with the z. So the case with the z, again, this is the z. Okay, this is the z. So you have to check both of them to see that if you see, it's not the kind that, if you the projection would be just the result from here. It's going to be quite different. So you have two different C's. So you have to check both of them to see what would be the conclusion. From these two, you should get the range for the row and the range for the phi. Okay, so I'm going to try this one first. Say, okay, let's see what would happen if z is equal to the 16 minus x squared minus y squared. You know that this is going to be a hemisphere. So this would tell you that Okay, so this will tell you that z squared is equal to the 16 minus x squared minus y squared. And if you move it to the other side, x squared plus y squared plus z squared would be equal to the 16. Okay, is equal to the 16, and you know that this is rho square, it's a sphere. So it's going to be a sphere, so that gives you that the rho square is equal to the 16. So rho equal to the 4. So that gives you the range for the rho. You know that the rho is behaving like r in the polar coordinates. So I have the data, I have the rho. So you need the phi. So, but we have one more condition on the z. Okay, any question? So try one more condition on the z to see if that give you the restriction for the phi. So the other condition is that the z equal to the x squared plus y squared. Now substitute from the polar coordinate, sorry, from a spherical coordinate over here. Remember the formulas, substitute for all of them. Remember z was a rho, okay, was a rho cosine of the phi at the z, so substitute for the x and the y. Okay, so this is it. Remember the x was like a polar, a rho cosine of the, okay, cosine of the data, sine of the phi, all squared, because the x is adjacent side. And the y is a rho sine of the data, sine of the phi, all squared. You have to simplify this one to see if that gives you an equation to be able to find the phi. So focus inside, okay, simplify. This is the one that we did before. So you square it and simplify it, so that gives you rho squared, cosine square of the data, sine square of the phi. So that gives you rho squared, sine square of the data, sine square of the phi. And always we talked about it, we have the common factor here, the common factors. So you pull out the rho squared sine square of the phi. So the leftover is always 1. If you write it down right away, we accept it, of course. So that's going to be the 1. So this is going to be 1. Okay, this would be 1, and the leftover, okay. We already talked about it. The leftover rho is positive. Phi is generally between 0 and 2 pi, 0 and pi. So can consider to be positive. So this would be rho sine of the phi. We have no difficulty in taking the square root of the sine square of the phi, because the phi is going to be an angle between 0 and pi in general. Okay, so you arrive at the rho cosine of the phi equal to the rho sine of the phi. Rho is a non-zero number, and you know the rest. You want an angle between in which the sine and the cosine are the same. You know that you can divide by the sine of the data, so that gives you tangent of the phi equal to 1. And that angle is pi 4, 45 degrees. So this means your phi is going to be between 0 and pi 4. You see, that's why I like you to say it, because this problem is much different from whatever you did before. Any question? So if you are in a spherical one, because the nature of the limit for the z are all different, you see, it's not going to be related to the, those cross section that you have. So you have to work on it. You have to work to see what give you one part, one side give you the restriction for the rho, which end up with a sphere centered at the 0 with a radius of 16, and the other one we end up with that that the coin type. So you end up with the sine equal to the cosine of phi, sine of phi equal to each other, and the only angle that would satisfy this condition is going to be the pi 4. Okay, now we are ready to integrate. So you have everything you need. So you go back, this is your integral. So you are going to change it, but when change it to the spherical coordinate, you know that there's going to be a special extra term, Jacobian. That's a rho square sine. And then you'll be able to integrate. Okay. So I'm going to set up the integral. There you are. So the volume is going to be equal to. This is going to be 1, 2, 3. This is, I go with the phi here, which is 0 to pi 4. It doesn't matter, put the data or phi, I do with the phi here. Then I go with the data, which is 0 to 2 pi. Then I go with the rho, which is 0 to 4. Okay, extra term, Jacobian, rho squared sine of the phi for the spherical coordinate, and the rest are going to be just, we go with the rho first, so d rho, data, and then the phi. You can switch the data and the phi, it doesn't matter which one goes first. Any question? So at least the integral is not a difficult one to operate. You operate with the rho first, it's a number, so you end up integral of a sign, and it can be done quickly. Okay, so we go for it. We integrate respect to the rho first, that gives a rho cube over 3. So it's going to be 0 to pi 4, 0 to pi 4, 0 to 2 pi. So that gives you 1/3 of the rho cubed, and the rho going from 0 to 4. Then you get the sine of the phi, d of the data, d of the phi. Okay, substitute just 4 cubed would be 64. And you can pull out that 64. So it's going to be 0 to pi 4, 0 to 2 pi, 64/3 of the sine of the phi, d data, d phi, in the order that we write it down. Pull out the 64, so that gives you 64/3, because you don't need it. So it's going to be 0 to pi 4, 0 to 2 pi, sine of the phi, d of the data, d of the phi. So when integrate respect to the data, everything else is constant. So the integral would be data only. So it's going to be 64 over 3, 0 to pi 4. Okay, it's going to be data, sine of the phi, if you like. But data is going to be from 0 to 2 pi. We can switch the order, just do the phi first. This is the way I write it down for this one. Okay, so when we're done, we come back and integrate respect to the phi. So 2 pi is the only one, data 0. So that gives us a 64 over 3, 0 to pi 4. Okay, then the 2 pi, sine of phi, d of the phi. 2 pi is the number, you can put it out. So that gives 128 pi over 3, integral from 0 to pi 4. Okay, and the sine of the phi, d of the phi. Okay, integral of a sine, negative cosine. So this is going to be, okay, that gives you negative cosine. So 128 over 3, and this is going to be negative cosine of the phi, going from 0 to pi 4. Substitute. So it's going to be negative 128 pi third. Okay, so it's, if you substitute for each one of them, so I just put a bracket here. So it's going to be negative cosine of the pi 4 minus negative cosine of the 0. Okay, you know that the cosine of the 0 is 1. Cosine of the radical 2 over 2 is going to be cosine of the pi 4. So we get the negative 128 pi third times it by negative radical 2 over 2 Okay, and this is going to be a positive 1. And it's the same answer. You can pull out the 2 here, and then you put them together. Okay, if you like to get the same answer that we created. So the common denominator is this one. So you can simplify the 2 and the 128. So that will give you, okay. So I have the 64. It's a negative 64 pi, okay, pi third. Pi third times it by a negative radical 2 plus 2. Okay, I just check to see where did I get this, and I think this negative sign is positive because the 128, we didn't do anything with the 128. So this would be positive, and this is positive. It must be the same answer. Okay, negative 2 radical 2. Some people, they write it down as a 64 pi third 2 minus 2 radical 2. So the volume is going to be this one. Okay, so this must be the same. That's it. 64 pi third 2 minus radical 2, and 64 pi third 2 minus radical 2. Okay, so it's a very, very nice problem, and you learn quite a lot really when you do this problem. That's why you see it. You see it all over the places. So make sure that those cross sections at the beginning is very important, to get that. The projection into the xy plane, it's x squared plus y squared to the 8, not x squared plus y squared equal to the 16. Okay, so we're done with the cylindrical and the spherical coordinates. Okay, so we check all the possibilities, but we usually give you something that's going to be quickly done. But it's very important to set up the integral. You see, just read carefully these. These are the very nice examples that we give you. And there are a couple of more. To practice is just the practice test that we have, and we take care of it on Thursday, and they are part of your final review. So the only thing new for the final review is whatever we do on the quiz 4. Everything else is already done. So study this quickly, then at least you are prepared for the 6 questions for the final, which is coming from this one, and the other 6 are coming from whatever you do on the quiz 4. Okay, 6, 6, 12. Okay, I give it a break now because we have one more section to cover. You see, whatever we did over here, it's kind of change of variable or substitution method, if you like. We change it. We change the variable from x, y, z into the new one, r data, etc. So it's a change of variable. But you can do this one in general, going back to the calculus 1. Remember the substitution method? We want to know what would happen to the substitution method if you bring it into the function of 2 variables or even 3 variables. So that's quite interesting one. If you know that one, these are just the results. In some books or some courses, they take the one that we did so far as that change of variable, and then they don't consider the general case. But we are going to consider that one, because especially if you're measuring physics or engineering, you are going to use it. Okay, so it's almost 11:45. So we come back about 12. Then I give you that last section of this chapter, section 14.8, and you get one question of change of variable on this test and on the final. It's easy, but it seems to be complicated. That's why I want to explain it carefully. The method that we apply it is short and quickly you'll be able to do it really. So it's like Lagrange multipliers that at the beginning seems to be complicated. But if you do it quickly, you'll be fine. Okay, so we finish everything today from that chapter. That's it. See you at 12 o'clock. Okay. So what we're going to do is kind of a substitution method for the double integral or triple integral or change of variable. Okay. So this method in calculus 1, we use change of variable method, okay? And we refer to it as a substitution method. So let's see what is going to be the version of this type of ideas for the double integral, okay? Let's bring it up. Okay, this is section 14.8. This is the last section that we're going to cover from chapter 14. So 14.8. So a change of variables, if you like, for the integrals. So it's going to be change of, as we did it so far, change of variables. Change of variables or substitution method, if you like, or substitution method. Substitution method, of course, for multiple integrals, double or triple, multiple integrals. Okay, that's going to be the one. We already done a kind of substitution method when you, or the change of variable when we change the rectangular coordinate into the spherical one or cylindrical one. Let's remind the idea that we are going to copy or extend from calculus 1. Okay, so start with this example. We review this one first. Okay, so review what we did before and what we are going to do now. Okay, for the review, we would like, for example, to evaluate this integral. Evaluate 0 to 1, very popular example from calculus 1. Okay, cube root of 1 plus 7x dx. You see, you want to evaluate this one by substitution method. U subs or substitution. Okay, substitution method. So you know that the solution is going to be, we're going to rewrite it. It's going to be 0 to 1. Okay, so we have 1 plus 7x, everything to the, okay, everything to the 1/3. Okay, 1/3 dx. And then we use the so-called U substitution. We take the inside to be U. So that gives 1 plus 7x. Okay, so, and then we find the differential of the U, because we have to find the dx. So the du is going to be, derivative would be 7 dx. And we solve for the dx, which is going to be the du over 7. Then we go back and we substitute. But it's going to be a definite integral. So you have an extra job to do. The extra job is going to be, you have to take care of the range of the integration or the limit of integrations. Because when you change a variable from the x to the u, then integral depends on the u, so you cannot use the 0 and 1. So you have to get these numbers. You see, when x is equal to the 0, then you put over here, so u would be, okay, you substitute, u would be 1. And when x is equal to 1, so in that case, your u would be 1 plus 7, which is equal to the 8. So then you realize that your u is going to be, you see, your x is between 0, 1. So you transform it into the u to be between 1 and 8. Okay, so it's, you know, it's kind of the change that you're going to have. You see, this is going to be the xy coordinate, if you like. This is going to be your x, if you like, and this is going to be your y. So you have this portion 0, 1. This is the range for the x. Okay, so we change it into the new system, if you like. In this new system, so what we do over here, you see the x is going to be just u axis, if you like. So this is going to be your u axis. So this portion of the 0, 1 would be changed into the portion of 1 and 8. So this is going to be 1, for example, and this is going to be 8. Okay, so we say it's a kind of a transformation that take this portion, the image of this portion is going to be 1 and 8 on the other side. So that's very crucial for us, this interpretation, because exactly we do the same thing. So in order to find that, we just get the vertex, if you like, the endpoint of the interval. So the endpoint is going to be 0 and 1, and we check it's going to be 1, 8. So a straight line goes to a straight line. Okay, then the rest are going to be just the algebra. We start with the given one. Okay, so you have the 0, 1, 1 plus 7x to a third dx. So now the integral is going to be with 0, 1 would be changed to the 1, 8. Okay, that would be 1, 8. And 1 plus 7x is the one that you call it u. So it's going to be u 1/3. Then you have extra term, if you like. That extra term is going to be this dx that you have. You have the du over 7. Okay, which is the same as, kind of, this is u to the 1/3, and you have the 1/7 du, if you like. That's the extra term that we are going to create in a minute for the function of several variables. And now you can put it out. So that would be 1/7 integral of u to the 1/3 du, going from 1 to 8. Then it's going to be 1/7, 1 up, 3, 1/3 plus 1 would be 4/3, 4/3 going from 1 to 8. Okay, so we just use the reciprocal. It's going to be 1/7. Reciprocal of 4/3 would be 3/4. U to the 4/3 from 1 to 8. So that gives you 3 over 28. And the u to the 4/3 from 1 to 8. You substitute. So if you substitute, they're going to be 3 over 28. Then it's 8 to the 4/3 minus 3 over 28, 1 to the 4/3, which would be just 1. Okay, so 8 to the 4/3, 8 to the 1/3 would be 2, 2 to the 4th would be 16. So that gives you 3 over 28 times 16, and that would be only 3 over 28. So the first one gives you 48. So that is going to be 48 over 28 minus 3 over 28, which is going to be 45 over 28 as the final answer. Okay, this is a substitution method, or the change of variable for the function of one variable. Okay, so it's like, going from one side to the other side. We change it, but the help is going to be the function that we introduced over here. You see, that's the u equal to the 1 plus x, 7x. This function, this equation can also solve for x in case you need the x. Okay, and so any question? Now we're going to set up this identity, or this method for a function of 2 variables. So our function would be a function of 2 variables, x and the y. So when you do the substitution method, you have to do something to change the x, something to change the y over here. Okay, and we have to take care of this extra term that we have. So let me just explain it, that how we're going to do it. First, this extra quantity that you have over here, This extra quantity, we refer to it as a Jacobian. So we are going to extend this one into the Jacobian, and the rest are going to be the same when you do the substitution. But you must take care of that extra term that you have, okay? So let's check this one. We're going to set it up when we get to the general term. Okay, now we have to introduce that portion first, that extra term, Jacobian. Have to know this one by name, Jacobians. So let's see where you need it, that extra term. Again, we recall that the general for the function of one variable again. Recall that the integral. Okay, we want just to generalize it so we can see it. The integral from a to b, f of x dx, can be solved by substitution method, can be solved by substitution method. Okay. Substitution method. Now, how are you going to solve it? That's the notation that we're going to extend. Now, if x is going to be g of u, a function of u, or u function of x, all of them are the same. You can use the inverse function to put it the other way around. And this is going to be your x, so you put the xg of u, then you have to find the dx. And the dx, we do it the other way around. D of x, just chain rule, is going to be g prime of u. Okay, times the du. Then this integral would be changed, you see, integral from a to b. F of x dx is going to be equal to integral of f of g of u. Okay, and the dx is going to be g prime of u du. It's the same thing that you do usually. But as I talk about it, you have to take care of this a. You put the a, replace the a by x if you like. So this is going to be, a is going to be g of something. Okay, we call it CD. CD. Okay, CD where a is going to be equal to the g of c, and b is equal to the g of d. It's just the other way around. It's the same thing, that you start with the x, then you find the corresponding number for the u, if you like. So we switch the variable at the same time we switch the limit of integrations. Now we're going to copy this one for the function of two variables. So instead of f to be f of x, we change it to the f of x and y. Then you need two substitution, one for x, one or for y. So the two-dimensional version, if you like, double integral is this: if z is equal to the f of x comma y, a function of two variables. Of course, it's going to be continuous to be integrable. Is a continuous, okay, continuous function on the region, because the domain is going to be a subset of r squared. Okay, it's going to be a continuous function on the region, let's say R, region R. And now the change of variable. Suppose we replace the x by a function of two variables, g of u and v, and y. This would be given to, or you are going to find it yourself, h of uv. So in practice, you need the U and the V. U and the V would be given to you. Then it's kind of like, it's a kind of an inverse function that we introduce the X and the Y. Okay, if this is going to be the case, then the copy of this formula would be, okay, if this is going to be the case, then the copy of this formula is going to be the double integral of the f of x comma y dA on R is going to be a double integral, but we switch. It's going to be f of, switch the x into the g of u comma v, the y into the h of u comma v. The region, of course, would be a change. We call it S if you like, because this region is among the related into the xy coordinate. So we change the coordinate into the uv. But that extra term that we talk about it, that extra term, we call it Jacobian. You got it to be positive, so it's going to be absolute value of Jacobian of uv that I'm going to introduce it in a minute. Then, of course, the du dv. So this means you do the substitution as you did it for the function of one variable, but you have to take care of this extra term that you have. You see, anytime you change because of those differential of the, you see, this is the extra term that you got over here, g prime. So the extra term is going to be for the function of one variable. What is this and how we're going to introduce it? Where a g of j of the uv is going to be called, it's called the Jacobian. Okay, that's it. It's going to be the Jacobian. Okay, sometimes say Jacobian determinant or just a Jacobian of, okay, Jacobian of coordinate, we call it coordinate transformation. Transformation, and this is it, x equal to the g of uv and y equal to the h of uv, because you transform the xy coordinate into the uv coordinate. That's it. That's going to be the idea that we are going to have. Okay, so what's the question? Is that the term? No, this is not determinant. This is just the absolute value that you're going to have. The inside one would be a determinant. That's why I just put the absolute value. No, sometimes they use this type of notation, but no, I'm going to introduce the Jacobian of u and v is going to be determinant of a matrix. And then you find it, you have to use the absolute value. It must be positive at the end. Okay, so GUV is called the Jacobian of a coordinate transformation, x and y, and is defined by, that's it. So the Jacobian of the u and v is going to be now the determinant of this matrix. So the matrix is going to be rho x, rho u. This is going to be rho x, rho v. Okay, rho x, rho v. And the second part is going to be rho y, rho u. And this is going to be rho y, rho v. Determinant of this matrix, okay? And you know that this is going to be, just emphasize that this is a determinant. So it's going to be G of uv, okay, which is going to be equal to, that's it, finds the determinant. It's going to be rho x, rho u times rho y, rho v minus the other way around, rho x, rho v times the rho x, rho u. Make sure you write it down, correctly. Okay, it's not going to be a big deal even if you drop this absolute value, because the result would be just, sometimes the sign would be different. Okay, so in this notation, sometimes they use this notation in your book. Okay, but I go with that. You see, or the notation that they use is Jacobian of a u comma v is equal to rho of x comma y, rho of u comma v. But you have to know the formula. You get this one done. Okay. Yeah, Jacobian is just a determinant. Yeah. Yeah. Anytime we talk about the Jacobian is a determinant of this. It's like the one that you use for the second derivative test. We call it Jacobian. Yeah, you can drop this absolute value if you are uncomfortable about it. It doesn't matter. It must be multiplied by the Jacobian. Okay, so that would be the extra term that we are going to have. So what we are going to do is we are going to just find the Jacobian of some of these famous transformation that we know it. You know that the famous one is the transformation that we used so far, the substitution. We use the polar form, remember? We transfer into the polar coordinate, we transfer into the cylindrical one and the spherical one. Then for those three variables, we have to extend it. Let's get one example to get to know it. Okay. It's just for function of two variables, we can extend it. So let's remind you what we did so far. Let's say get this example. This is going to be the example that we have. So we'd like to find the Jacobian, for example, for the polar coordinates. Find. Okay, find the Jacobian. Jacobian is a name, great mathematician, Jacobian for the change of variable. Change of variables defined by polar coordinate. Remember when we find the area, we talk about that extra r. The transformation are x equal to the r cosine of the data and the y equal to r sine of the data. Okay, let's find the Jacobian of this one. So the variables are x and the y. The change of variables are r and data. So the solution is going to be, that's it, finding the Jacobian in terms of the r and data. The new one is the determinant of, I just repeated, rho x, we have r and data. So rho x, rho r, okay, rho x, rho data. Second part, rho y, rho r, rho y, rho data. That's your Jacobian. So differentiate Jacobian determinant of derivative with respect to the r, that gives just cosine of the data. Derivative with respect to the data would be negative r sine of the data. Remember the first one, both of them are x. Second one, y. With respect to the r would be just 1. We get the sine of the data. Sine of the data and derivative with respect to the data, derivative of sine would be cosine. So that gives you r cosine of the data. Any question? Get the determinant. You know that cross multiply. So that gives you r cosine a square of the data minus cross product okay, is going to be negative r sine square of the data. So this is going to be r cosine square of the data plus r is, sorry, that's it, yes. And this is going to be r sine square of the data. You factor out the r, so that give you cosine square plus sine square. This is 1. So the extra term would be r. So Jacobian of r and the data is equal to the r. Remember, when you use a double integral, when you use the polar coordinate, that extra term that you use, remember, that extra term that we used was r. Remember, r dr d data. So we just remind you that, note that the polar coordinate, this is it. If you have a double integral, and if you want to change it to the polar form, this is it. You get the new region. You change the x into the r cosine of the data, remember? R sine of the data. Jacobian is going to be Jacobian of r and the data times the dr d data. But Jacobian is r. So that would be simply the double integral f of r of cosine of the data, r sine of the data, and r dr d data. And you know that this is the one that you've been using. So it's the kind of, as I told you, in some books that they just don't refer to this because they said they already done it. So why we should do it again? Any question? What class of maths you should take for more on the Jacobian transformation? Jacobian transformation is coming from time to time vector analysis, and that's the one that you will see. And yeah, that would be vector analysis is the one that you will see the Jacobian. Jacobians happen in different places, okay? But you know that calculus 3, we do as much as we can with this vector analysis part or the vector part, but it can be extended if your discipline is going to be especially in physics. You need more, so you can change the formulas to get these numbers. But there are some special problems that we use it. But it's a symbol for the time being for this class. It's just we summarized it here. But when we get a function of several variables, of course, this is a function of 2 variables. We can do all of this in a Euclidean space function of n variables. Then the role of these notations are coming. Okay, so this is of course one application of this. If you do something like partial differential equation, you will see again this type of things. Okay, it's going to be all over the places. Okay, so just to confirm you that the connection we can do, this is of course the Jacobian for function of 2 variables. Okay, it can be extended to the function of 3 variables. I prefer to talk about the 2 variable first, then we can go with the 3 variables as well. Okay, to get it. Let me just give you that 3 variables as well, because the example that you have is spherical coordinates. Okay, so if you want to extend the Jacobian if you want to do the substitutions in triple integrals, you need your Jacobian to be following. Okay, so we focus on the function of 2 variables for integration, but we extend this Jacobian notation for you, that you are interested in. So what's going to be, if you like, a substitution, but we are not going to, for the integrations we already done a spherical coordinate. That would be the good examples, if you like, but you need the Jacobian. A substitution in triple integrals, just checking the spherical coordinates, okay. You see, you want to do the triple one, everything would be the same, except you are going to have your x is going to be, you see your transformation is going to be your function of, let's say, gu, v, and w. This is going to be your x. Then the same thing, your y is going to be a function of u, v, w. Like the spherical coordinate, you have what? You have that, okay, you have the rho, phi, and data, if you like. And the z is going to be k of u, v, and w. So the structure is going to be the same, but you have to find that Jacobian. If this is going to be the case, your Jacobian would be Jacobian of the u, v, w is going to be equal to, you have three variables, x, y, z. So it's going to be the determinant of this matrix. So on the first row, you go with the x. So round x, round u, round x, round v, and the round x, round w. That would be the first row. Then the second one would be the y. So it's going to be round y, round u, round y, round v, round y, round w. And the last one, of course, going to be round z, round u, round z, round v, and the round z, round w. See, there's going to be a Jacobian. So it doesn't matter how many variables are going to have. You can do this one all the time. Again, we are not going to use it, but I just check the polar spherical coordinate for you. Or you can use the cylindrical or the other one, it doesn't matter. So, for example, let's check the cylindrical. If you get time, I do the spherical for you. Find it's easier. Find the Jacobian for the spherical one. The algebra involved is much more. Find the Jacobian for the cylindrical. Okay. For the cylindrical coordinates. You know that's going to be r data and z. That's easier. Let's do this one. You know that in this case, your x is r cosine of the data. Your y is r sine of the data. And your z is just z. So you have to use this formula. Okay, let's do it. So your Jacobian is going to be now, what is going to be the Jacobian of r data and z? Is going to determine of this matrix. So the first row we go with the x. It's going to be like the one that we did. Okay, derivative respect to the r is cosine of the data. You see that's what the cosine of the data respect to the data was a negative r sine of the data, but respect to the, okay, that's going to be x respect to the r, respect to the z, and respect to the z. There is no z here, so that would be 0. Okay, look at this one. UVW. So in this case, it's going to be R data and Z. The second one, the same. With respect to the R would be sine of the data. Respect to the data would be R cosine of the data. And respect to the Z, there is no Z. And the last part, you respect to the z, there is no z here, that give you 0. There is no z here, and that give you 1 only. 1 only. And if you find this determinant, you know that you can use the last row as the, as the definition that we have. So we get all zeros. So this is going to be, okay, I'm going to use this one. So this is going to be 1 times cross multiply this. If you cross multiply, that give you r cosine square of the data, and that would be plus r sine square of the data. You know that this is going to be 1. This is going to be r. So the Jacobian of the r data and z is equal to the r. Okay, you can check the polar coordinate is very, the spherical coordinate is much more involved, so we are not going to use it. So our job is not just to finding the Jacobian. We want to get a real example to see how we're going to use that substitution method that we're going to have. Okay, so I'm going to give 2 examples. Your tricky part is when you switch from the xy coordinate into the uv, that the limit of the integrations is the one. And that's a tricky part. Otherwise, the rest are going to be easy, and the integral is going to be easy one. Okay, so let's check. Any question? Again, not big deal. You already got the cylindrical one, but it's nice to know it. Okay, these transformation types arguments. So let's check the first example that I'm going to give you. Sometimes the transformations are on triangle as we did it before, and the rectangle, trapezoid, etc. So I'm going to explain just 2, and we give you 1. It's going to be easy question, the way we are going to describe it. Okay, so let's see what you want to do. You want to evaluate this integral by substitution method. They give you the variable and the instruction. Evaluate this integral. Integral is from 0 to 1. Okay, 0 to 1 minus x, radical x plus y times y minus 2x whole squared dy dx. You see, in that kind of integral that you like, to find it. So what we would like to do is by substitution method or change of variable. By substitution method, okay, and we give you, sometimes they don't give you the one that you substitute those variables transformation, but we are going to give you that by substitution method or change of variable method using using the following transformation. So the transformation are the following: u equal to x plus y, this one, and v equal to y minus 2x. I say that's a problem. You know that when you substitute that, give a radical u, and that give v squared, then you can easily integrate it. But your difficulty is going to be this limit of integration. It's like the one that we did before, remember, for the type 1, type 2. So let's see how you nicely set up these problems quickly to be able to do it. First thing to do, you have to find the Jacobian. Remember, so solution is going to be, okay, solution is going to be, your first part is, so you change your variables into the u and the b. So the first part is what is going to be Jacobian of the u and the v. In order to do the Jacobian, you need x and y. Remember, you differentiate x respect to the u and the y. So in order to get to this one, so you have to find what is the x and what is the y. Sometimes they give you this format, but not all the time. So what you have to do, a little bit of algebra. So you have to put these together like a system of the equation. So we have the u equal to the x plus y. Then v is equal to the y minus 2x. Okay, is a system of two equations, and you solve it for x and y. Okay, so I just remind you that solve for x and y. Okay, substitution method, or addition method will do it for you. So in this case, I'm going to eliminate the y. So this is it. I multiply one of them by a negative sign, okay, to take care of it. So I multiply this one by a negative sign to eliminate the y. So I have the u equal to the x plus y. So this would be a negative v equal to the negative y plus 2x. Okay, I just multiply by a negative 1. Now, if I add them together, so the y would disappear. So I got the u minus v equal to the 3x. So that give me the x. So x would be u minus v over 3. So that give me the x. Okay, I need to find the y. You can do the same thing, or you can use substitution to get it. This is x, so you substitute in the first part, for example, to get it. It depends, which method are you going to use. So I'm going to use this one. So I have the x plus y equal to the u. Then I have the x here. Okay, I just substitute. So the x is u minus v over 3 plus y equal to the u. So the y would be u minus v over 3. Common denominator would be 3. So that gives me 3u. Okay, I apply this negative sign, minus u plus v. So that make it into the 2u plus v over 3. Okay, so that would be y. So my y is equal to the 2u plus v over 3. This is going to be the y. Okay, because it's a true system, so you have to have all the information. Okay, so there you are. You can write down as is, or you have to differentiate it. So what I do is this is going to be x, which is u minus v over 3. If you like, you can call it u third minus v third to differentiate. It doesn't matter really if you don't do it. So that gives you 2u plus v over 3, which is a 2u third plus v3. Okay, so this is going to be a relationship between these. Now we are ready to get the Jacobian. Any question? So find the Jacobian of that extra term that we need. Okay, so we go with the Jacobian. It's Jacobian of the u and the v. So remind ourselves that this is it. The first part is going to be round x round the u. And this is going to be round x round the v. This is the round y round u. And this is the round y round v. Okay, that's your formula. Substitute equal to the Jacobian of round x round u. This is it. Round x round u, that give only 1/3. So that give you 1/3. Okay, 1/3. Round x round v. differentiate respect to the v that given negative 1/3, because this would be 0. Negative 1/3. Okay. Go for the y. Y. Round y, round u. That give you 2/3, 2/3. Okay. Round y, round v, 1/3, 1/3. Okay. Cross multiply to get the determinant. So it's going to be equal to, you multiply these two together, 1 times the 1/3, 1/3 would be 1/9, minus, you multiply these two together, that give a negative 2/9, negative 2/9. Okay, negative would be positive. So we get the 1/9 plus 2/9, which is a 3/9. And the 3/9 is 1/3. It's positive and we don't need any absolute value. So the Jacobian of UV for this problem is simply 1/3. Okay, that's a step 1 for these problems. Sometimes they give you X and the Y in terms of the U and the V in your book, but we don't, because we give you the actual substitution. So you have to solve, you see. This algebra part is part of the deal that you have to do it. Because you want to differentiate X in terms of the U and the V in the Jacobian. So you have to have the X and the Y. So you have to do this one to get this true. Okay. Any question? Now let's see what we have and what's going to be the next step. You see the next step is going to be the limit of integrations. You know that you go from this, you see this is the one. You go from this into what? Into the UV. So you have to see what's going to be the limit of integration. Like the function of one variable that I did. So this is going to be your challenge. Your challenge is going to be the limit of integrations. So you check to see what we have. Okay, this is a transformation that we have. You say that in XY plane, in the original XY plane, you're integrating, you see, look at this one. So your X is between 0, 1, your Y is between 0 and 1 minus X. It's like, you know, the type 1, type 2 that we did. So this is a situation we're going to have. So we have the X between 0, 1. Okay, that's your X. And you have the Y between 1 minus X. Okay, this is the situation that we have. If you graph it, so what is going to be the graph of this? You know, if you want to graph it, so the line is, okay, you take the Y equal to the 1 minus X. And if you want to graph this one, this is X and this is Y minus X at this point, the partition point. So if you put X equal to the 0, sorry, Y equal to the 1 minus X. If you put X equal to the 0, Y would be 1. And if you put X equal to 1, Y would be 0. So this region is going to be this one. Okay, so this is a 0, 0, 0, 0, 1. And this is 1. Okay, then 1 and 0. And this is going to be 1 and 0. And this is 1. So this is going to be the line. So the region that you integrate is this one. So this is your region in the XY coordinate. So your X is between 0 and 1, and you just pick the, okay, in your integral, it seems to ask that you pick the type 1 region, if you like. Okay, this is going to be your type 1 region to get the result. Any question? Now, when you change it, you transform it into what? Into the, instead of the XY plane, you go to the UV plane, if you like. Okay, so what would happen to your region if you change it into the UV plane? Because you change the variables, remember? You change the variable from the X and the Y to the U and B. Because you should be able to find the restriction for you. Now, this is the one that, in different books and even in your book, they talk about it differently. But the point is, we do it exactly as we did in the format of the function of one variable. Remember, the thing that we're interested in was these vertices, if you like, you see, of this triangle. So you have 3 points, if you like, you see. Consider that these vertices that we have. Okay, note that the vertices of that region, of the triangle or the region of the region in XY plane are, what is those crucial points? You have the origin 0, 0. You have the 1, 0, and you have the 0 and 1. So find the corresponding points into the UV plane. Then that'll give you the idea of what is going to be on the region in this case. Okay, remember they are X, Y. So go to get these points into the UV plane. Okay, so find, if you like, I just explain it for you. Find the corresponding form, and that is going to be okay, corresponding points, if you like, in UV plane. So what would be 1 by 1? But remember the formula using, what is the transformation that you have? Your transformation is U equal to the X plus Y, remember? You transfer the region, you transform these points, and the Y was, this is it. Test these points 1 by 1. You get the 0, 0. So 0, 0 in XY coordinates. 0, 0. So in the case of the 0, 0, you have what? You have X equal to the 0, Y equal to the 0. So you put it here. So your U would be 0, 0. U would be 0, 0 plus 0. Okay, I write it down, you know how I get it. 0 plus 0 would be equal to the 0. And what's going to be your V? Your V is going to be, again, the same thing. Okay, it's going to be 0 minus 0, which is going to be 0, 0. So this point 0, 0 would transform into the, okay, so 0, 0 goes to the 0, 0. Okay, that would be the case with the 0, 0. Okay, any question? The other point is 1, 0. So you have the 1, 0. You can do it right away if you don't like to write it down. We don't mind, but this is, I'm going to explain. X is 1, Y is 0. So what's going to be U? U would be X plus Y is going to be 1 plus 0, which is equal to the 1. And V is Y minus 2X, 0 minus 2. That gives me negative 2. So the point 1, 0 going to the UV coordinate or the plane is going to be represented by 1 and negative 2. Okay? And similarly, the last point is 0, 1. So that would be the 0, 1. So in the case of the 0, 1, so X is 0. So X is equal to the 0. Y is equal to 1. So U would be equal to, remember U is X plus Y. So that gives 0 plus 1, which is equal to the 1. And the V would be Y minus 2X is going to be 1 minus 0. So that gives you 1. So that would give you a point. So this means 0, 1 would transform into what? Transform into the 1, 1. Okay, so this is it. You get a 1, 2, 3. These are going to be your critical points, if you like, when we go to the UV coordinates. So go back, identify this, and get the region in question. Okay, any question? It's a procedure that you have to do it the way in your book they're doing it. They use more algebra, and they just consider each line here, the sides of the triangle, and they transform it. But this method is easier or better, really. So let's locate this point in the UV coordinates. Okay, so what you have in the, so going to the UV coordinates, you see this is going to be the case. Now this is UV. Okay, the point that we got, I write it down here. I have a 0, 0. Okay, 0, 0, 1, negative 2. And I have, okay, what is the other one? I have the 1, 1, yes? 1, 1. Locate this point here. 0, 0. 1, negative 2. 1, negative 2, 1, negative 2. So that give me another point. Okay, then I have a 1, 1. 1, 1. 1, 1. I have another point. You see, these are going to be the vertices, if you like, of those triangles that are going over here. So this means if I want to get the image of this transformation, this is it. I'm going to have this one. You see, look at this. This is going to be a situation that I'm going to have. So in fact, that triangle that you saw over there, you see, remember, this is going to be the 0 and this is 1. This is going to be a 0, 1. So my region would be, my region is going to be this one. It's going to be the connection between these points. So this is going to be the image of that triangle that you did have in the UV plane that we're going to have. Okay, and now I'm going to describe this one. It's kind of type 1, type 2 region to get these numbers. And then as you can see, it's not going to be good if I go with to the right, to the left, because I have two different lines here. So the best way to do it is just U is going to be between 0, 1. Okay, so that can be U right away. U is between 0, 1. Okay, now I need to find, how about the V? Okay, remember the V is like the y-axis that we're going to have. So in order to get the V, you see V is going to be up, down, you see, up, down, up, down, up, down, up, down. So V is going to be between these two lines that are going to have. Okay, so it's going to be the V. V is going to be between these two lines. Okay, the bottom one is this one. The bottom one is this one, and this is going through the 0, 0. And this point is what? This point is a negative 2 and 1. Okay, the slope is a negative 2. So this line is going to be V equal to the negative 2U. Okay, that's going to be the one, because we have 2.00, the origin, and the negative 2 and 1. If you have any doubt about it, you can write the equation of the line. It's clear. How about this one? Okay, this is 0, 0, and this point is 1, 1. So this means this line is simply, the slope is 1. U equal to the V. So U would be between negative 2U and the U. So I can integrate it now. So I got the Jacobian, which is going to be the extra one. I have the limit of the integrations, u between 0, 1, and v between -2 and u. This is your challenge when you're dealing with this type of problems. Check the example in your book. You will see it's they don't explain it very well. I like this method. I get those vertices quickly. I can identify my, you just give me any of those, I can do it right away. So it's much better idea. But you can do some algebra, read the example in your book. Sometimes it would be confusing, but it's not bad. But I like this method. You transform those vertices, okay, the crucial point of your plane, if you plane in the XY and bring it to the U way, it always can be found easily. And of course, the region is not going to be complicated, the one that we're going to consider. Okay, now we are ready to set up an integral, if you believe it. So remember the integral was, but these ideas are going to be used in some more details, depends on what you want to do in future, really. So knowing it is very good. And this section is the best one. So 0 to 1, this is the original integral. 0 to 1 minus x, and it's going to be the square root of x plus y. The problems are very standard, so we are not going to miss it. We have no difficulty. Most of the people, they do it on the test. So this is the original one. We switch. Is switch into equal to, now what's going to be the switching one? The double integral. Now, as we know, the u is between 0, 1, so it's going to be 0, 1. V is between -2u and the u. The substitution, remember, this is u, so it's going to be radical u. This is v, so that gives you v squared, Jacobian. Jacobian of uv, and then we go with the v first and the u. But the Jacobian, remember Jacobian, we created as a 1/3. So 1/3 is not a big deal, so we can put it out. So we change this one into the 1/3. So we continue, the integral is going to be, integral is usually very easy to find. That gives you -2u to u. Okay, so I change this one into the u to the half. This is going to be v squared, Jacobian of the 1/3. Okay, and the dv du. So that is going to be the case that we continue. What's the question? You get this one. How did we know the orientation of the UV plane? What do you mean? We just got points. The point that we have, the orientation is going to be just the usual one that we're going to do counterclockwise. You see over here, the U is going to be between 0 and 1, have no difficulty. And, the lower line and the upper line. Okay. So you pull out the 1/3. So that gives us a 1/3 integral from 0 to 1, -2u to u. Okay, and it's just easy integral to go. Integral respect to the v would be v cubed over 3. And that will take us going. So it's going to be 1/3 integral from 0 to 1. So that gives a v cubed over 3. Okay, and there is a u to the 1/2, you keep it. You are going to go the v from a -2u to u. And then when we're done, we come back and du. Okay. So substitute these numbers. So we get a 1/3 integral from 0 to 1. If you put v, that gives you u cubed. Okay, u cubed over 3, u times 1/2 minus -2u to the 3rd over 3. and the u to the 1/2, then the du. Okay, so let's see. You simplify, go forward to get these numbers. You get it. How we know that? No, you see when we get these vertices over here. What's your question? V is no. It's XY coordinate. We change it to the UV plane. So your point, your plane, and what the XY. So you just change it to the two new variables. So basically, you go from the XY plane into the UV plane. That's always the way we do it. So it's a point. You see, the function is original function is f of x and y. In the statement of the theorem, we change it to the function of u and v. So that's a part of the deal that, when you get over here, this is going to be u and this is going to be v. Okay. And so so let's continue to take this one. You have to do a little bit of this simplification to the third u to the 1/2, just add them together. So this is going to be 1/3, 0 to 1. Okay, 3.5, which is going to be u to the, 7/2. So this is going to be u to the 7/2 over 3. And this would be -2 cubed would be -8. There is a negative here, +8. And that would be the same thing. You see u to u cube. So that gives you u to the 7/2 over 3. Okay, du. And then simplify it. 1 and the 8 would be 9. Okay, so this is going to be 1/3, 0 to 1. So that gives me 9 u to the 7/2 over 3 du. Okay, so everything would be simplified. So that gives you 1, that gives you 3, 3 and 3 would be 1. So you end up with the integral from 0 to 1, u to the 7/2, okay, du. And this integral is easy. So it's going to be u to the 7/2 plus 1, 9/2, and the 9/2 from 0 to 1. Okay, this is 0 to 1. So use the reciprocal 2, 9, 2, 9, u to the 9/2 from 0 to 1. If you put the 1, that gives you 2, 9. Final answer. Okay, it's very nice method to get these true. To get these portions that you're going to have. Okay, again, check the one which is in your book. But your book give you more details of those lines. You see, they find the equation of all the lines involved, but we don't need it. You just get those crucial points and put them together, and that would be the result. Okay, when you practice, you get a feeling of, just put them together really, and it's not going to be difficult to handle. It takes time a little bit. Okay, so any question? I should give you one more because this next one is important, because sometimes they describe the region. The original one is going to be maybe a triangle, but in your book, you have a couple of them that's a kind of a parallelogram, and you have a trapezoid. So I should give you this next example to get, just pick one of them. In fact, this is a kind that you have in your book, one of your assignment. I'm going to explain it to just make sure that you are going to be able to handle those type of ideas. Okay, I'm going to write it down. This is the one that I picked from one of the assignment that you have. You have this function a couple of times in your book, and you have it in your practice one. But this one, I changed this region so that you get the idea of, this type of region would be given to how we're going to handle it. Okay, so let's quickly get this one done, then we're done. We would like you to get different form so that be able to do it. And sometimes if you do complex analysis, and these type of ideas are going to be used over there too. So in complex analysis, we have a function, we call them conformal mapping, or they refer to it as a transformation. So you do these type of ideas. So it's not bad. Just spend a little bit time. Okay. And you need this one because all the assignment, you have it in your assignment, quite a lot of these ideas. Okay, let's see if you can do it. It's a famous function, so the function are going to be around, but the region, they would be different. Okay, so we may give it the same one, but we change the region. So let's see what is special about this one. You use the given. Again, if you see the solution of this type of problems in your book, it's quite a lot, but we can shrink it. Use the given transformations. Okay, transformations. Or, sometimes they say change of variable, but I go with the transformation. Change of variables. Same thing. This is it. Something like u equal to the x plus y again, and v equal to x minus y. Okay, we want to use this one to evaluate this integral. To evaluate the integral. And what's the integral? It's a double integral. It's e to the x plus y over x minus y. Okay, x plus y over x minus y, dA, region, R. But look at the R. Where is R? R is a trapezoid, where R is the, that's it, ideal, if you like. It's a trapezoid. R is a trapezoidal region. It's like when we say rectangular region with these vertices, with vertices. The vertices are the following: 1, 0, 2, 0, 0, -2, and 0 and -1. You see, that's why. That's why I want to get a feeling of when these information only would be given to you, how going to handle this type of problems. An example of your book is a parallelogram, and one of them is a triangle, but I picked this one. Okay, the first step. This is it. We need to find the Jacobian, so you have to solve this. Solve for x and y to get those preliminaries first, and then we get this one through solution. So let's go for that. So we would like to find the Jacobian. So you need the x, you need the y. Bring them in. So what you have? U is equal to the x plus y. V is equal to the x minus y. Okay, that would be easy. Add them together. So it cancels out. Okay, so you get what? You get u plus v equal to the 2x. So that gives you x. X would be u plus v over 2. And you can write down as u have, v have to, when you want to differentiate it, you feel comfortable. Okay, go back, substitute to get the other one. Okay, you can substitute in the first one if you like. This is going to be u is equal to the x plus y. Okay, so u would be u plus v over 2 plus y So the y would be v minus u plus v over 2. The common denominator give you 2. So you get a 2u minus u minus v. There's a negative sign. Make sure you apply it on both of them. So your y would be what? U minus v over 2. Minus v over 2. Okay. So again, you can write this one as you have. Minus we have. Okay. Any question? So now we can get the Jacobian. Get quickly your Jacobian. So it's going to be Jacobian of the UV. Remind yourself is around X, around U, around X, around V, around Y, around U, around Y, around V. Okay, that's your formula. Substitute. Drift of X respect to the U, that just give you 1/2. This part would be 0. Drift of X respect to the V would be 1/2 again. So that's a 1/2, 1/2. Drift of Y respect to the U, Y respect to U would be 1/2. Okay, Y respect to the V would be negative 1/2. Cross multiply. So, and that give you 1/2 times negative 1/2, that give you negative 1/4. Minus 1/2 times 1/2 is 1/4. So that give you negative 2/4, which is equal to the negative 1/2. Usually use the positive number for the Jacobian. Okay, so if you like, the absolute value is equal to the 1/2. So we use the 1/2. You know, if it's going to be negative, we just use the absolute. Any question? So now we have the Jacobian. Now the challenge is transformation of this from the XY coordinate into the UV plane. So let's see what we have and what we are going to get. Okay, are you ready? Let's go to the next page and check this. We don't have any equation, and I'm not going to find any equation. I do it right away. Okay, so this is it. So let's see what we have in XY plane, the original one, XY coordinate. So I bring the points that it's given. You see it represent with these vertices 1, 0, 2, 0, 0, negative 2, and the 0 and negative 1. Okay, I need only these points, but I'm going to graph it for you so that you can see it roughly. Again, I don't go with this equation. That would be enough just to get an idea. Locate the points that we have. We have 1, 0. 1, 0. That's 1 point. 2, 0. 2, 0. Okay, so that's a 1. This is 2. 0, negative 2. 0, negative 2. Okay, this is it. This is going to be 1, negative 2. So that gives you 0, negative 2. Okay, then 0, negative 1. So 0, negative 1. 0, negative 1. So I'm going to make a trapezoid out of this. See? So this is going to be the region. Okay, so this is the region in XY coordinates. Any question? So what I'm going to do, I'm going to drop this one, change it, transform it, okay, into the UV plane. So I have the idea, I have those crucial points. So I'm going to do the same thing, those transformation. Okay, drop it down. Go to the UV plane. Okay, find these coordinates in the tables of the U and the V. What is the transformation? Okay, that we have. You see the transformation is that the U is going to be X plus Y in this new format, and the V is equal to the X minus Y. Okay, pick each of these points, substitute to get the corresponding one for the UV plane that we arranged. Okay, so we start with this point. Point is 1, 0 in the XY. So this means X is equal to 1, Y is equal to the 0. So to go to the transformation, so that give you U equal to the 1 and 0 would be 1. Okay, V equal to the 1 minus 0, that give you 1. So the result would be the point 1, 1. That's the first one. Any question? Check another one, 2, 0. 2, 0. In the XY coordinates, 2, this is the 0. Again, U would be X plus 5, 2 plus 0, which is 2. V would be X minus Y, 2 minus 0, which is 2. So that gives you the point 2, 2. Okay. The third point, 0 and negative 2. So X is 0, Y is a negative 2. So U would be X plus Y, 0 minus 2, which is a negative 2. And the V would be X minus Y. X minus Y would be 0 minus negative 2, which is 2. So you arrive at a negative 2 and 2. That's your third point. Last point, 0, negative 1. Go to the, this means X is 0, Y is a negative 1. Going there. So your U would be X plus Y, 0 minus 1, which is a negative 1. And your V is X minus Y. So it's going to be 0 minus negative 1, which is going to be 1. So that gives you the point negative 1 and 1. That's it. So locate these points into the XY coordinate, UV plane if you like. So to get the idea, what type of region do you have for integration? It's going to be quite interesting, this one. Okay, locate the points. 1, 1. 1 and 1. So this is the first point, 1, 1. Next, 2, 2. 2, 2, 2. So that give you 2, 2. The second point. Negative 2, 2. Negative 2. 1, 2. Negative 2, okay, and 2. So this is going to be negative 2 and 2. Okay, then a negative 1 and 1. Negative 1. Negative 1 and 1. That's it. So this is going to be the region into the UV coordinates. So you see, this is going to be your region that you have to be concerned with for the integrations. And you pick the integral. So you have to decide which region are going to go for it. You're going for the type 1, type 2. Okay, just think about it. This is going to be a region. If you want to go with the x is between -1 and 2, then you have to go vertical, which is no good. Because vertically, you see here, you have to consider these two lines. The line is going to be different, so it's no good. So you better, okay, you better go from left to right, you see, left, right, left, right, left, right. You have these two lines. So you better fix the y. The y is going to be constant. You see your y start from, okay, so your y start from here, which is 1, okay, and end up here, which is 2. So your y in this case is v, of course. So your v is, you fix the z, v between -1 and 1, okay. So for you go to the right, to the left, best choice. You see, right, left, right, left, right, left. So if you go to the right and left, okay, this is going to be your u. So you are going to be between right and the left. Let's see what you have. When you go to the right and the left, okay, so this part, what type of lines is this one? You know that this is 1, 1, and this is 2, 2. 1, 1, 2, 2. So this line is just u equal to the v. So this line is just simply v equal to the u, okay, that you have. And this line over here, remember this is going to be -2, 1 and the -1, 1. So this line over here is going to be simply v equal to the -u. So as you have this is it. So your u is going to be between what? Between a -v and the positive v. Nicely, we can integrate it. Okay, that's the best thing to do. You know, that's crucial points, show you how to do it. Again, some people, they do lots of algebra to connect them together, but this method is a very good one. Okay, so we are going to integrate it. Jacobian extra point is, what was the Jacobian? Jacobian is 1/2, so we put them together and we find our integral. Okay, what's the question? To get these numbers true. Is in between 1 and 2? Yes, you are right. Yes, you are right. Thank you. Yes, is the v is between 1 and 2. Thank you. It's going to be 1 and 2. Excellent. That's it. Yes, this is between 1 and 2. Very good. And the other one is correct. Okay, so we are going to, we put them together, integral is going to be straightforward. Okay, so nice to know these type of problems. Okay, and then you should be able to do all of them. So let's find the format. I don't know whether I finish it or not. Yes, I have it. So this is it. So what is the original one? Remember, the original one was this one. Double integral on the region R, and the function was e to the x plus y over x minus y. Okay, that's the original one. So we change it to the notion of, our notion is going to be, say, double integral. And this is going to be starting from -v to v. Okay, then we get the 1 to 2. Okay, 1 to 2, so e to the, so the top one is u, and the bottom one is v. Okay, then we have a Jacobian, our Jacobian, and we integrate respect to the u and the v. You know, it's always the absolute value of a Jacobian that we use it in this formula. Okay, so the Jacobian was 2, the absolute value was 1/2. So we can pull out the 1/2 and start integrating. So it's going to be 1/2, 1 to 2, -v to v. So this is uv. Okay, uv du dv. Now you have to integrate it. You want to integrate respect to the u. You know, exponential function never change, but you have to have the u prime. So if you differentiate respect to the u, so u prime would be 1 over v. So the 1 over v is missing, so it's going to be 1/2 of 1 to 2, negative 1 to v. It's like e to the uv divided by 1 over v. When okay, when u is going from negative v to v, and when you're done, it's a dv. Okay, because it's a number. It's like when you integrate e to the ax is e to the ax divided by a. Okay, now reciprocal give you v here, so that give you 1/2 of the integral from 1 to 2, negative v to v. So that is a v e to the u v, but the u going from negative v to v, then the dv. Okay, substitute for u. So it's going to be 1/2 integral of 1 to 2, integral from negative. I made a miss here. So as soon as I integrate it, sorry, you don't need this one anymore because we're just integrating. Okay, this is it. Okay, so sorry, this is it. We're just working on this number. We did the first part of the integrations. Okay, so I'm going to substitute to get it. I have to put the u equal to the negative v. So it's going to be messy, but not bad. If you put u equal to the v, so that give you vv, I write it down for you, minus v e to the, it's going to be negative vv and the dv. Everything would be simplified, because that give you 1/2 integral from 1 to 2. It's going to be v times e, because these two would cancel out. Okay, and these two would cancel out. So you get something like, something like e minus ve to the negative 1 and dv. Okay, you can factor out the v, the rest is just a number. So it's going to be 1/2 1 to 2 v times e minus e to the negative 1 dv. Okay, and you pull out those. Okay, it's going to be e minus e to the negative 1 over 2, integral from 1 to 2 v dv. And integral v dv would be, of course, dv squared. So that gives e minus e to the negative 1 over 2, and that's a v squared over 2, and finding from 1 to 2. Okay, so this is going to be kind of e minus e to the negative 2 over 4. Then the v squared going from 1 to 2. If you substitute, it's a e minus e negative 1 over 4. That gives you 4 minus 1. 4 minus 1 would be 3. So that gives you something like 3/4, if you like, of e minus e to the negative 1, the final answer. Okay, so that's a substitution method for the function of two variables. Okay, as you can see, it's different, but it's not bad. But with the idea of how you put them together, and it's going to be used. We are not going to use it, of course, for the rest of the course, because we already done we already done cylindrical and the spherical one as an example. That's it. So we are ready for our test 3. But what I do is tomorrow I start talking about chapter 15. Okay, chapter 15 is going to be new format, if you like. We extend the function. Our function so far, the domain of the function was in R2, R3. The range of the function was a number. So what we're going to do is we are going to go full course. The domain of the function would be R2, R3, and the range of the function would be a vector. So the range can be also in R2 or R3. The result's going to be called a vector field. So we introduce those functions. We talk about the derivative integral for the rest of the course. And in engineering disciplines and the physics, you need chapter 15. Okay, all of them are going to be used. So all these preliminaries was in order to take care of those. Okay, And they are new, but there is going to be a connection between these classic steps and the last one. It's a beautiful chapter, really, and we have time to do it. Okay, so I do the chapter 15. The first section is all formulas, so we can talk about it tomorrow. Even then on Thursday, we give you time. I go with the practice test number 3 that I posted. And then after your test, we have time to finish those section of the chapter 15. Okay, that's it. Have a good one. Let me know if you need anything. Study these carefully, okay? And start working on the test 3. We give you the solution on Thursday. Okay, have a good one. Bye-bye.